Is our lesson over the definite integral. So again, just like with the first section, not as much as the first section, but still definitely enough here. I'd highly encourage you to take a moment to read the actual textbook that is on Google Classroom, or probably more importantly, read some more pages on Calculus for Dummies, okay? Because that's going to help you understand kind of the vocab that I'm using and give you more of the information about finding these definite integrals. Okay, a couple of things I want to note on this page besides the learning objectives. We have if a function is continuous over the interval a to b, then f is an integrable function on that same interval. Okay, so that's a key thing, is like if your function is continuous, then your function is integrable. Okay. All right. Let's try doing one real quick. All right, now I'm actually going to show you guys, because I know you guys got mad at me in the derivative unit when we went the long way on how to find the derivatives. So I'm going to skip the long way on how to find the definite integral, and I'm going to show you kind of the fast way. All right, so what we're going to learn in a couple lessons is that one part of the fundamental theorem of calculus states that if you try to evaluate an integral over this interval, right, this interval right here is, change to drawing. This interval is 0 to 2, okay? And this function is continuous. X squared is continuous, so we have an integrable function, all right? Ultimately, when you look at this, all right, we're looking at the fundamental theorem of calculus would tell us that if we find the antiderivative, right, so that capital F of x, if we evaluate that antiderivative at 2 and at 0 and subtract them, we will find the value for this definite integral. Okay? A couple things I want to point out. The 0 and the 2, right? You've never seen numbers. This is the first time you're seeing numbers on this. 0 and 2 are called the limits of integration. All right, I don't want you to confuse that with like our use of the word limit back in the first semester, but 0 and 2 are kind of the constraints or boundaries of the integration we're doing. And the letter dx is called the variable of integration because we're just using x, all right? But that's called a dummy variable because you don't really do anything with it. So essentially what I'm going to do here is, based on our work at the end of the first semester, we're going to find the antiderivative of x squared, and then I'm going to evaluate that at these two endpoints, these two limits of integration. So if I'm trying to find the integral of x squared, right, that's going to, I know it has to be x cubed because the derivative of x cubed is going to give me x squared, but I don't want 3x squared, so I have to put that 1/3 in front. Now, remember when we used the plus c before, all right? The reason that we don't have to worry about it now is because if we had that c, whether we picked 2, so like plus 6, plus 7, minus 8, whatever the number is, when you subtract, they're going to make 0. So that's why we don't have to worry about the plus c in terms of evaluating this definite integral. So now I'm going to do 1/3 times 2 cubed minus 1/3 times 0 cubed. So whatever this is gives me the value of my definite integral. All right, so obviously 0 cubed is going to be 0. 0 times 1/3 is 0. So this is just really just focusing on this first piece here. 2 cubed is 8, so this is going to be 8/3. So that is the definite integral value from 0 to 2 of x squared dx. Now, let's talk about finding the net sign area. All right, so I'm going to go to Desmos and show you what happens when you graph this linear function and look at the x-axis over the interval -3 to +3. So we have y equals 2x, we're at y equals 0 for the x-axis, and we're looking at between between -3 and 3. So here's -3 right there, and then +3 right here. Okay, so if you look at the area underneath the curve here, you'll notice that some of it is going to be positive and some of it's going to be negative. So let me draw a sketch for you. So there is y equals 2x, and we have until +3 to -3. And essentially, what this creates is we have Oh, I want to change colors now. There we go. All right, so we create this area, which is the negative part, and this positive area, and we're trying to find the net sign area. So what this means is we're going to be using this formula down here, which is essentially to find the area of the first piece, which is always going to be in the positive y values, and the area of the second piece, in this case in the negative y values, and we're going to subtract them. And we should notice is that my areas here, or my shapes here, are triangles, and we know the formula to find the area of a triangle, right? That's going to be 1/2 base times height. So essentially, to find the net sign area between -3 and +3 of 2x dx, we're going to find the area of this first triangle and subtract the area from the second triangle. All right, so let's see. Our base is going to be 3 for both of these. Right, both of these bases are 3. And then the height is going to be 6 for both of these. All right, so the area when your base is 3 and your height is 6 is going to be 9. And because they have the same dimensions, when we subtract 9 minus 9, we get a net sign area of 0 units. Okay, very similar problem here, finding the total area. Just the only difference is that when we find the total area in this part of the equation right here, we're going to look at essentially taking the absolute value of that function, which just means that instead of subtracting them, we're going to add them. All right, so in this case, I'm going to find the absolute value of this linear function is going to be the area of the first shape plus the area of the second shape. All right, so again, I'm going to go to Desmos and graph this line, x minus 2, and the x-axis over the interval 0 to 6. I should have kept that one. Keep that one. This one's going to be x minus 2. I'm looking at 0 to 6. There we go. Okay, so you can see that, again, we create two triangles here. This first one's a little smaller than the other one, so we're not going to have equal areas. And you'll notice the first triangle here between 0 and 2 is actually the y values are in the negative position. The other triangle between 2 and 6 are going to have positive y values. But because we want the total sign area, we're actually just going to add these areas together. Okay? So when I look at the base here, this one is 2, a height of 2. This base is 4 with a height of 4. So they actually have the bases and heights are going to be the same. So let me draw a sketch for you. All right, so we have our line, y equals x minus 2. All right, remember this is 0 all the way to 6, and we're creating, as we just showed, two triangles. Kind of a smaller one first with negative y values, and then a larger one with positive y values. All right, the base of this one is 2, the height is 2, this base is 4, and this height is 4. Using the same idea like the last one, where the area is 1/2 base times height. That means we're going to find the area of my first triangle, which is always the positive one, and this is the area of my second triangle. I'll do that. Let me get that back real quick. Undo. We come back? Excellent. Okay. So essentially, this is the area of the second one. There we go. I'm going to have area of the first one is 8, right? 4 times 4 is 16, divided by 2 is 8, plus the area of the second one, 2 times 2 is 4, half of 4 is 2. So this total area, all right, between x minus 2 and the x-axis over the interval 0 to 6 is going to be 10 units. Okay, now, here are some properties that we're going to be looking at for the definite integral. And again, all of these are in your book, and they're in the Calculus for Dummies section on integrals. I'll just run through them pretty quickly here. If you look at the first one, you notice that the limits of integration, right, those endpoints on the integral are the same. If that ever happens, then that's always going to be equal to 0. For 2, if you switch those limits of integration, so switch a and b, all it does is it makes your integral value the opposite. And then for 3 and 4, you'll notice that if we're using the sum or the difference, we can just break them apart into 2 separate integrals and add them. And in 5, if there's a constant in front of your function, you can move it to the front. And then in 6, this one's a little tricky, but we'll talk about it in one of our examples, that if you put a number c, most of the time you'll put it between a and b, but it actually still holds true even if the values for a and b and c are not provided, or they're not like in the order. If you break it up into smaller pieces or different chunks, then you can still add them together to get the same thing. Okay, so let's try this one. This one says to express the definite integral of this cubic trinomial over the interval -2 to 1 as the sum of 3 definite integrals. So let me start with just one integral from -2 to 1 of -3x cubed plus 2x plus 2 times dx. Okay, so I'm going to break that up into 3 separate ones, where my first one is -3x cubed dx plus another integral, 2x dx, and our third one, which is 2 dx. Now, the very last thing to do is to take these constants that are in the first two and move them in front. So you'll have -3 times the integral of x cubed dx plus 2 times the integral of x dx. And then this one actually stays the same. A lot of students will probably think to move the 2 outside, but there's no actual value after, like variable after that 2, so you actually have to leave that inside with the dx. All right, so this is the answer for this example. Okay. Now, very similar, or we're going to use another property, that very last property that I said, that if you kind of break up your interval by using a number in the middle, that you can, or your integral, I should say, that you could actually find that other value. So in this case, I'll show you what I mean. We're talking about from 0 to 8 of f of x dx can be equal to the integral from 0 to 5 of f of x dx, and then the integral from 5 to 8 of our function, right? So this would be a true statement. Well, we know this one is 10, and we know this one is 5. All right, so this one right here, right, solving for it, has to be equal to 5. So the integral from 5 to 8 of this function must be equal to 5. Okay, one more problem talking about finding the average value, and all we're doing to find the average value of a function is you're still finding the integral, right? So the value of the definite integral, but there's one more thing you'll have to do, all right? So that this right here, you're going to have to multiply whatever you get for your value for your definite integral times 1 over b minus a. So you essentially subtract the endpoints in your interval and do the reciprocal of it, and whatever that is multiplies by your value of your definite integral. So let's find the average value using this function x plus 1 over the interval 0 to 5. All right, so what I can do is I can find, let me go to Desmos and sketch it for you. I'll do it two ways. I'll do it the way without using the knowledge of the fundamental theorem of calculus first, and then I'll use the fact that we actually can do this using that fundamental theorem. So we have, it was x plus 1, yes, and we're looking at 0 to 5. So if you look here with the x-axis for the y equals 0 back again, right? Remember, from 0 to 5, which is 5, 6. All right, I'll sketch the shape, because it may not be as easy to see it when it's on a triangle or a rectangle, but essentially, I'll do it right here. We're talking about from 0, 0, 1 to 5, 6. And with the x-axis, I don't know if you see it, but this actually creates a trapezoid. I know it's been a long time since you've thought about trapezoids probably, but the area for a trapezoid is 1/2 times the height times base 1 plus base 2. All right, so in this case, our height is going to be 5 units from 0 to 5. Our base 2 is going to be 6 units, right? That's 0 to 6. And base 1 is going to be 1 unit. Okay, so I can find the area using that formula. All right, so let me write this down. So the integral of x plus 1 dx is going to be whatever this area is, which, let's see, 6 plus 1 is 7. 7 times 5 is 35, but half of that is going to be 35 halves. Now, that's not the answer because now we need to take this 35 halves and multiply it by this 1 over b minus a. So now I'm going to multiply times 1 over b minus a. Let's find that. 1 over b minus a is the same as 1 over, let me write my endpoints on my integral here, from 0 to 5, is 1 over 5 minus 0, which is 1/5. So if I multiply 1/5 times 35 halves, I'll get my answer, which is going to be 7 halves is the average value of this function. Now, if I were to do this using my understanding of the fundamental theorem of calculus, right, 0 to 5 of x plus 1 dx, the way that I would do this is I would find the antiderivative of x plus 1, which is going to be 1/2 x squared plus x, and I'm going to evaluate that for 5 and for 0 and subtract them. Now, it's nice because when you have 0, that's all just going to be 0. So really you're just focused on this piece right here. 5 squared is 25. So that's 25 halves plus 5 over 1. Changing that denominator gives me 10 halves, which gives me 35 halves. Shouldn't be surprised by that, considering we found the area of that trapezoid to also be 35 halves. All right, and then the next step of multiplying that by 1 over b minus a is no different. You still get 7 halves for the answer. All right, guys, so that's it for the discussion about the definite integral. Don't forget to try some of those homework problems.